Okay, so the final exam will be cumulative, and it will cover the materials from lecture 1 to lecture 19. And actually, we have first midterm cover the resistor interconnect to the semiconductor physics, and the second midterm covers material from the transistor to the CMOS inverter. And then the materials after the second midterm will be the standard scaling rule and the memory technologies. So roughly, the materials before the, let's say in the first midterm will be like 25% of the final material. And the materials between the first midterm and second midterm will be another 25%. And the materials after the second midterm will be about 50% of the final exam material. So that means the focus will be the standard scaling rule and the memory technologies. But of course, we have questions here in the semiconductor physics or the MOSFET or the CMOS inverter. So let's go through the abilities that you are expected to have for the final exam. So firstly, in the first lecture 2, we talk about the interconnect made of metal, such as aluminum and copper. So you should be able to calculate the resistivity of the metal. And how is that be calculated? So the conductivity of metal is, let's say, sigma, and sigma is equal to n q mu. N is the electron density of the metal, q is the electron charge, and mu is the mobility of the metal. And the resistivity, is 1 over sigma, is 1 over conductivity. And secondly, ability to perform the calculations based on the basic semiconductor equations like the Fermi function, and then relating the electron hole density to the band model, like the EC, EV, EF, and the ability to draw the band diagram of the intrinsic N-type and P-type semiconductor, given the doping density. So this part is important, and let's discuss that. So this is one important concept we discussed in this class. So you need to understand the doping, N-type and P-type doping, and how would that relate to the band diagram. So in the silicon, we have the conduction band and valence band, and in between is the band gap. So electrons are in the conduction band. Holes are in the valence band. And we have the Fermi level. And Fermi level for the intrinsic semiconductor, which means you don't have doping. Intrinsically, the Fermi level will be in the middle of the band gap, and we also call this EI. So that means at this level, the probability to find the electron is 0.5. And then with the doping, we will move the Fermi level. For example, if you have N-type doping, then the Fermi level will be closer to the EC and farther away from the EV. And we care about the distance between the conduction band edge EC and the Fermi level EF. And this distance can be calculated from the equations we have here. This one, this is if you know the distance EF minus EC, you can calculate the electron density. Or if you know the electron density, then you can back calculate the EF minus EC. But typically, the electron density will be known first. The reason is that if you do the N-type doping, the electron density will be the same as the doping density, your donor density ND. That means you can back calculate what is the distance between the EF and the EC. So if you do that, then this, let's call it delta E. This distance, let's say EF minus EC will be KT natural log ND over NC, because you know electron density equals to doping density ND. So this is for N-type. And in this semiconductor, what is the hole density? You can always use this NP product, because no matter what kind of doping, N times P always equals to Ni squared. Ni is the intrinsic carrier density. So you can always do that. And then what is intrinsic carrier density? In the silicon, it's 1.5 times 10 to the power 10 at room temperature. So this is intrinsic carrier density. And you can always use that. N times P equals to this Ni squared. So this is the energy band diagram. I think this is important. You should be able to draw this kind of energy diagram and also calculate the distance. And I show the example for the N-type, but you can also do the P-type, which the EF is closer to the EV. Okay, so this is the energy diagram. And then understand the mechanism of the drift and diffusion current in semiconductor and the Einstein relationship. So this is about the transport of the carrier. There are two ways to move the carrier, electron or hole, in the semiconductor. One way is to do the drift, and drift happens when you have electric field, and you know the motion of the electron or hole depends on the electric field, and the velocity here of the drift, velocity of the drift equals to the mobility multiplied by the electric field. And then diffusion is different. Diffusion is when you have different concentration of the electron or the hole. For example, in one region of the semiconductor, you have higher hole density. The other region has less hole density, so the hole will diffuse from the high concentration to the low concentration. And this is the diffusion current. So if you look at the current, you have two components here. But those two components are not independent. There is an Einstein relationship between the coefficient drift dn with the mobility mu_n, and then the coefficient here is the kT over Q, which is thermal energy, thermal voltage. So what is thermal voltage? Thermal voltage at room temperature is 26 millivolts. Okay, so this is electron hole, let's say drift and diffusion. And then after that, we move to the p-n junction. We have p-n junction in the MOSFET, right? If you look at the NMOS, the source and the drain are N-type doping, substrate is P-type, so you have p-n junction between the source to the body or between the drain to the body. So in the p-n junction, understand the current flow is unidirectional, the IV, and also the band diagram. So in the p-n junction, we have this kind of IV. When you apply voltage to the P side, if the voltage is positive, then you will have exponential increase of current. And if you have negative voltage to the P side, then the current will be very small and will saturate to this I0 negative. And the current equation is like this. Let's say over kt. So this equation describes this IV relationship. And also for the p-n junction, we can draw the band diagram. So the p-n junction will have this kind of band diagram, P and N. And for the equilibrium state without any external voltage, we will have a single Fermi level. And this side is P because Fermi level is closer to the valence band. And on the N side, the EF is closer to the EC. So here we have a built-in barrier, VBI. The barrier height is given by this equation, depends on the thermal voltage and the doping NAND over Ni square intrinsic carrier density. So this is p-n junction. And then after p-n junction, we have the MOS cap structure, MOS, which is a vertical direction in the MOSFET structure. From the gate to the channel, you have MOS structure. So in the MOS structure, then understand we will have the inversion of the channel. And then we will have the threshold voltage to trigger this inversion. And then calculate the threshold voltage. So let's look at this from the energy band diagram. So this is the MOS structure. We draw it like this. Let's use NMOS as example. So for the NMOS structure, the substrate will be p-type. So you have this EF close to the EV. So MOS. For the metal, you only have a single Fermi level. And then this is without voltage. You have a land Fermi level here. Now you want to create the inversion of the channel. So that means the surface will become N-type. So this is P-type. And you want to create the channel, which is N-type. So that means the surface needs to be inversion. That means you apply positive voltage to the gate. And we discussed many times, positive voltage to the band diagram means push down the band. So that means this voltage will be pushed down by your gate voltage. So everything will be bent down like this. So everything will be bent down like this. So within the semiconductor, you still have a single Fermi level here. At the inversion, let's say the threshold condition is when the surface potential here, what is surface potential, is a bend down of the band at the surface. This is a phi s. This phi s equals to 2 phi b. So what is phi b? Phi b is the distance between the intrinsic Fermi level and the EF. So this is a phi b. Or here, let's say this is phi b. So when you reach the threshold condition, then the phi s equals to 2 phi b. Or in other words, if you look at the distance, let's say this delta E, this is delta E1, and here we have delta E2. Let's draw it. So this is a delta E2. So as the threshold condition, this delta E1 also equals to the delta E2. In other words, this delta E1 will determine the electron density at the surface. Delta E2 here will determine the hole density at the bulk. So the threshold condition is defined when the surface electron equals to the hole at the bulk in terms of density. So you have this relation. But this is not the gate voltage you apply. It's not this 2πb, because the gate voltage Vg is dropped across the oxide and semiconductor. So you have another Vox here, which is voltage drop on the oxide, then plus this bias. So this is the energy band diagram in the MOS structure. And if you look at the threshold voltage equation here, it has this first term correspond to the Vox, and the second term 2πb correspond to the phi-s. And then you can use the parameters to calculate the threshold voltage, which depends on the dielectric constant and the doping density, and phi-b and Cox, which is the gate oxide capacitance. So this is the MOS structure. Any questions? So here I think this MOS structure diagram is important, and you want to review the homework relating to this, and also we have similar questions in the first test. So we have those related examples.